Hello everyone, I hope you're all doing well. I'm going to consider a very brief conceptual example to talk about the resultant moment about a point. Okay, we will of course solve numerical problems on this idea once again. Okay, all right. So consider a thin, long beam. Okay, which is pinned at a certain point. Okay, pinned at point O. Of course, this beam is not in equilibrium, which is okay. I'm not interested in the acceleration of the beam and so on. I'm not interested in the weight of the beam as well. I'm going to assume that the weight of the beam is fairly negligible. Okay, so assume the beam has a negligible weight. Compared to the forces acting on it. Okay, and so I'm going to draw this thin beam as you'll be seeing here. Okay, so here is a beam, and I'm going to say that there are two forces that are acting on this beam. One is a nice simple force, as you're going to see. Okay, so here is the beam, here is the pinned point of this beam. Okay, this is a pin support, as you might have seen in one of my other concept videos. Okay, now I'm going to say that there is a force that is acting on this beam in the following manner. This is your regular force. Okay, I'm going to call this force as the force F1. Okay, and it's acting at that particular point, which is the point A. Okay, and this is the point of interest for me, the point which is called as point O. Okay, that's the point of interest. All right. Then what I'm going to say further is that there is another force that is acting in the following manner. Okay, so this force is acting as shown here at a particular angle to the horizontal. Okay, it is acting at an angle of theta, some arbitrary angle, and I'm going to say that this force is of magnitude F2. Okay, and it's acting at the point B. Okay, and I'm going to say that distance from point O to point A to point B are the following distances. Okay, so distance from point O to point A is the following, and then from point A to point B is also known to me. Okay, so that's another distance. So these are the distances. I'm going to draw them in a minute. Usually when I draw distances, I draw them using dotted lines. Okay, so I will continue that particular idea here too. So this is a distance d1, this is a distance d2. Okay, so this is distance d1, this is distance d2. Okay, what do I need to find? I need to find the resultant moment about the point O due to these two forces. Okay, so obtain the resultant moment about the point O due to forces F1 and F2. And this is of course a two-dimensional problem, so I'm going to set up a coordinate frame which I'm going to call as the following. So my x, y and z directions. Okay, so here is one of them. Then I'm going to have another direction that I'm going to be drawing out here. Okay, so I'm just showing you the direction, and I'm going to get rid of it in a minute and say that just this line that I'm extending here is the other direction. Okay, this is my second direction, and my third direction that's coming out of the page as I'm showing here. Now I'm going to call this as x, and this is y, and so the third direction is going to give me z according to the right hand rule for coordinate frames. Okay, so these are the x, y and z directions. So the unit vectors along these directions, as you know, is little j. Then the unit vector along this direction is little k. I guess I'll scoot that down and draw it here. Okay, so that's going to be little k. And then the unit vector along the x-axis, I'm going to draw it parallel to the x-axis as little I. Okay, it just signifies the direction of the x-axis. Alright, so here is the situation. Basic idea for resultant moment is the following. So key idea. Resultant moment about a point is the vector sum of the individual moments due to the forces. Okay, the resultant moment about a point, I should say resultant moment vector, is the vector sum of the moments about that point due to the individual forces. Okay, which means that the moment O, if I call it as the resultant moment, this is going to be the moment about the point of interest O due to the force F1 plus the vector sum. Okay, moment about O due to the force F2. Okay, so this is a vector sum. It is not a scalar sum. It is similar to what you have been doing all along, right? When you're doing Cartesian 2D and 3D vectors, you're just taking vectors and adding them up vectorially, right? How do you do that? By breaking them up into components, and that's exactly what I'm going to be doing here, okay? But first, let me employ the following idea for that, okay? So first things first, I see that this force F2 is at an angle theta. So I'm going to break that force into its components along the x and the y directions, and watch this very carefully. Okay, so as I break the force into its components, you see that here is the point of application, which is the point B, which means that when I break it up into components, I want to make sure that the components are also acting at that point of application, okay, on the actual physical body. So which means that I'm going to have one component of that force which is going to be acting vertically down, and another component of that force which is going to be acting horizontally and to the left. And it is fairly straightforward to see that this is going to be F2 times sine theta, and then this is F2 times cosine theta. Okay, which means that I'm going to have this force F2 replaced by these F1, F2 sine theta and F2 cosine theta, and I'm going to redraw this figure once again. Okay, so I'm going to take this entire figure, including all of these axes, and copy that and bring it onto the next page. And what I'm going to do further is, okay, I'm going to get rid of this force F2 because I have already broken it into its components. Okay, so I'm going to get rid of that force F2 because I have taken it up and broken it up into its components, which are F2 cosine theta and F2 sine theta. Okay, and let me maybe draw this component a little better down here. Okay, so I'm going to cut that off, and I'm going to say, okay, here is F2 cosine theta, and here is my x-axis, which we had extended. So this was acting along the x-axis, and the unit vector along that direction was little I. Okay, I'm going to make use of the scalar approach to solve this particular problem. Okay, so scalar approach. To solve this particular problem. Okay, what am I going to do here? I'm going to say, okay, magnitude of the moment due to the force F1. What is that going to be? That is going to be the magnitude of the force times the distance, right? The perpendicular distance. And do I know the perpendicular distance from the point of interest, okay, which is the point O, to the line of action of the force? The perpendicular distance, as you can see that I'm drawing here, is going to be the distance d1. Okay, which means that this magnitude is going to be F1 times d1, or let me fill it up in the color that I'm using for the moment. So this is F1 times d1. Okay, and then its direction what is the direction of this moment. If I use the right hand rule, align fingers of your right hand with the force F1, your palm faces the point O, curl your fingers, direction of the thumb, right? Which means that this is going to be directed in the following manner. It's going to be having a counterclockwise swirl about the Z direction. Okay, it is going to be counterclockwise about the Z direction. About Z, which means that I can now use these two and then write it as a vector. Okay, I can now say that, okay, moment O about the point, moment F, moment of the force F1 about the point O as a vector is F1 D1 times K. Okay, and so this is going to be the moment MO due to F1. I hope it is clear so far. Then here is another thing you can notice. Look at the force F2 cosine theta. If you look at F2 cosine theta, if I take the force and then if I extend its line of action, it intersects the point O, as you can see, right? If I take this particular line here and if I just extend its line of action, it intersects the point O, which means that there is no perpendicular distance you can find between the force F2 cosine theta and the point O. That is fantastic news. Okay, so I'm going to do that here next. Look at F2 cosine theta. If we extend its line of action, it intersects the point of interest. Okay, which implies there is no perpendicular distance between the point O and the force F2 cosine theta where it acts on the body. Okay, so which means that we come across, so this implies first of all that the moment due to the force F2 cosine theta is actually equal to 0. So a very, very important point that comes out of this is the following. So important, if line of action of a force intersects the point of interest, then there is no moment about that point due to that force. Okay, that's a fairly important statement and something that will help us solve problems very quickly. Okay, I'm going to just see, okay, if I extend the line of action, does it intersect the point O? No, it does not. Then there is a moment. Does it intersect the point O? Yes, it does. Then there is no moment. Okay, so which means that this force F2 cosine theta can be completely discounted from the proceedings. Then I look at the force F2 sine theta. If I look at that force, I see that, okay, what is the perpendicular distance from the point O all the way to where the force is acting? And you can very easily see that that is going to be the distance D1 plus D2, right? And so I go to the next force, which is F2 sine theta. So that's my third thing that I'm going to be doing. So moment about the point O due to F2 sine theta, I'm just using the magnitude, and that's going to be the force times the perpendicular distance. As you can see here, the perpendicular distance is D1 plus D2. Okay, so this is the force times the perpendicular distance, d1 plus d2. This is the magnitude. Okay, and in the previous case also, this was the magnitude. Okay, and then how about the direction? Okay, now you got to be careful. You got to be very careful and follow along with me. Take the fingers of your right hand, align it with the force F2 sine theta. Align it such that your palm is facing the point O. And you will find out that, okay, this is going to be a little tricky. I'm going to have to turn my fingers around such that my palm is facing the point O. And you'll feel a little bit of pain, okay? Which is good, because this is telling you something important. If I take the fingers of my right hand, align it to this force F2 sine theta, and my palm is facing the point O, my thumb is actually going to be pointing into the page, which means the direction of that moment is directed along the negative z-axis. Okay, so I'm going to draw that in a different color. Okay, before that, this is getting a little too crowded. So this is the z direction, and here is the direction of the moment due to the force F2 sine theta. Let me get rid of some of these things here. Okay. I'm going to cut that off and redraw my z direction again without the arrow on it. Okay, so here is the z axis. Okay, and the unit vector, of course, along the z direction is known to us as a little k. Okay, that's from before, so let me do that again. Okay, so this is the unit vector little k. These little lines always cause a large amount of misery when I'm drawing them. I don't know if you have felt the same thing. Alright, so small things are the biggest issues, right, usually. Alright, so I have the moment due to that force pointing in the negative z direction. So that's going to be moment about the point O due to the force F2 sine theta. Okay, so once again, take the fingers of your right hand, align it to the force F2 sine theta. Your palm, important thing is your palm should be facing the point of interest. And then you curl your fingers, your thumb is going to be pointed into the page. Okay, so this tells me the following. Okay, the force, this is about, this is directed along the negative z-axis, which means that this is a clockwise moment. And in the previous case, this was a counterclockwise moment, right? Directed about the positive z. Okay, this was about along the positive z axis. And so if you have a clockwise moment, you obviously see it's going to be a negative, which means that if I write this as a vector, MO F2 sine theta, this is going to be minus F2 sine theta times d1 plus d2, but in the k direction. Okay, so this is the second one, and here I had the first one. Okay, which means that the resultant moment is the following. Okay, so resultant moment is MO, resultant is MO due to the force F1 plus MO due to the force F2, but then we broke this down into MO due to the force F1 and then MO due to the force F2 cos theta, MO due to the force F2 sine theta. Okay, and then we realize that, okay, hey, this cos theta creature does not do any harm to our lives, and so this is going to be F1 d1 in the k plus minus F2 sine theta d1 plus d2 in the k direction, or the negative k direction, or I can combine things together. MO is f1 d1 minus f2 sine theta d1 plus d2 in the k direction. And depending on the magnitude of f1, f2 and the distance and the angle, this resultant moment can be positive or negative. Okay, so this can be positive or negative. Okay, it depends on f1, magnitude of f2, the angle theta, distance d1 and the distance d2. Okay, and if it's a positive moment, then it is directed along the positive z axis because it is directed only along the k direction. If it is negative, it's directed along the negative z direction because it's pointing only in the k direction. Okay. All right, so this is the basic idea of resultant moments. The same thing, we use the scalar approach in this problem to calculate the magnitude. That's why I said the scalar approach. But then essentially this is still vectors. Okay, even though we are using scalar approach, we are using the idea of vectors. Okay, so even though we are still using the idea of vectors. Even though we call it as a scalar approach. Okay, scalar meaning that you're using your hands to notify the direction, and then you're observing the figure to see, okay, what are my perpendicular distances and so on. Okay, so basic idea is resultant moment is the vector sum of the individual moments. Okay, and then this is the same as what you've been doing for forces, except that moment has a magnitude and a direction. And how do you find the magnitude? How do you find the direction? That's the key thing here. All right. I hope all of you are staying safe. Take care of yourselves. Bye bye.